Let's get to it. Welcome everyone to my defense. It has been a long 5 years, and I am grateful to be here in front of you all talking about what I've been up to. The title of my dissertation is applying how we can apply user cognitive skills and inferable belief states to human-robot teaming. And we're going to be exploring these topics in depth today. So I want to start with the question, when my clicker starts working again. Okay, there we go. What makes a teammate? This is a question many of my coworkers have asked people in presentations, and I thought it's very relevant to what my work is in. Specifically, I'm looking at what is the difference between a teammate and a tool? What are the capabilities? Where is that delineated? And it's a very, there's a bit of a debate that's been going on the past couple of decades about what makes a teammate. And we're specifically looking in the context of human robot and human AI teaming here. So most robots that work with people today really ignore the person. They treat them as a surface level embodiment in their environments that navigate, move things, but don't really look at them more in depth. And so if a person asks a robot in most of today's systems, hey, can you help me? The robot will reason about that. They'll say, they will think, I heard this string of text, can you help? I observe a person, I observe a table. I assume that that's what the person is looking for help with. However, that treats things as a rather surface level. And over the past couple months, I've been thinking about what is the difference between a teammate and a tool. And I've completed a bit of a litmus test, where if you replace the human teammate with a capable automaton, would the performance of the team change? So if you take the human, replace it with something that looks like a human, might act like a human, but is a robot, would it actually change the team? And my outcome of that is, if yes, the team's performance changes, it's likely a teammate capability. It's using some aspect of the human to inform its own decision-making and be a teammate. Alternatively, if no, then it's likely a tool capability. And we'll explore this a little bit further and how it applies to my work. And so if you think through what makes a teammate, a couple ideas might come to your mind. One could be bidirectional.
We lost the display.
Okay, thank you. It would not be a defense presentation if not for these sort of issues.
I can see it.
I can see it too.
Yeah, it's not on the screen. It's not in the Zoom window anymore.
I still see it.
That's weird. It totally went away from me. All I see is Jack and the screen behind him.
Try scrolling.
Oh. Okay, got it back. All right. Sorry.
All right, great. So you might think of bidirectional communication, where the teammate is working with your level of knowledge to communicate, to set goals, to do informed communication that's really intentional. You might think of a teammate capability as maintaining a mental model of using a theory of mind or projection to inform its own actions and planning. You might also think of shared authority over key decision-making. And this is, for human-human teams, is something we do all the time, but there are ethical concerns when you have a robot that might have authority that's higher than you. Might be able to override your decision or make a decision based off what it perceives your reasoning capabilities to be. And fourth, you could consider a teammate as a being with intentioned communication, to know what and when to communicate and to do that effectively to support the team's objectives. And each of these four characteristics are characteristics of teaming, and they go beyond what we normally consider a tool. And I find that they're all linked by this understanding of an individual model of a person. They model the person's beliefs, intentions, capabilities, and use that to inform decision-making and task coordination. And this leads me to the research question of my defense. How can robots model and apply a user's cognitive state, and cognitive state referring to this concept of an internal representation of a person, to inform human-robot teaming capabilities? How can robots model this cognitive state and apply it to inform downstream teaming capabilities? My work has explored this question among a number of projects, some more on tool behavior, some more on teammate behaviors. And I've had fantastic collaborations with people all over departments here at GT. And today I will be focusing on 3 of these works. All of them, or many of these works, apply to human-robot teaming and explore different aspects of this. How can we use cognitive skills, look at situation awareness, monitor cognitive workload, look at strategic styles, But today I'll really be focusing on 3 of my first author works. The first one you've seen previously, it's the work I did prior to my proposal. And the other 2 are looking at world belief states. It's my proposed work and what I'm excited to share with you all today. So the structure of this talk, we will first look at what is cognitive state, defining that on a terminology that we can ground to the other works. We'll then look at predicting future performance at robot teleoperation tasks. This was my pre-proposal work. We're going to breeze through that one. And then we're going to go into the works I've done since my proposal last February, looking at how we can infer the situation awareness of users, and then our follow-up work to that, which is bringing it from a 2D domain to a 3D domain, and looking at level 1 situation awareness or belief states. Let's begin. What is cognitive state? It's a messy question, and researchers throughout the human AI teaming and human robot interaction communities have used this term cognitive state quite loosely. But I find that there are really 3 areas that are deemed cognitive state, or that cognitive state is used to mean. The first being cognitive skills. These are latent skills that people hypothesize can be translated to different tasks. So if you're good at, say, spatial reasoning, and you then do a task that requires a lot of spatial reasoning, you'll be good at that task as well. The second area people consider cognitive state at is workload. And this is an area that I know Julie Adams does quite a bit of work in, and is looking at how systems can monitor a workload passively and then use it to adapt interfaces, adapt teaming, and make this a real-time adaptive autonomy. And third, people use cognitive state to refer to mental models, our understanding of an environment. How can a robot infer that or use that to enable theory of mind and the resulting team fluency related activities? My work is not the first to look at cognitive state. In fact, cognitive state has been looked at in different forms for about 30 years now. And research in this space has been rather sporadic. Researchers have looked at different aspects of this, but not really how they can work together or even cohesively as a broader research effort. So research in the space has been very sparse. And as such, there have been several major gaps in each of these 3 core areas. How can we use cognitive skills actively in robot operation or as a predictive power for role assignment and so on? How can we use biometrics to passively monitor workload? Every year at HFES, there's a paper saying, we did it, we can monitor workload, followed by a paper that says there's no correlation whatsoever, it's not significant, and that debate has been going on for quite some time. And third, looking at mental models, how can mental models be obtained by robots? How can they be used? How can we unlock novel team capabilities through theory of mind? And that area is really just starting to be looked at. My work has explored several or all of these gaps in some form. And today we're going to be focusing on the cognitive skills gap and the mental models gaps. And these are, again, 4 of my 5 first author works. Here's an anchor slide to situate what I will be referring back to as we go through this presentation. The dotted line denotes what my proposal was. So we're going to breeze through cognitive skills and then go into the research questions that we've looked at with inferring situation awareness and applying that to downstream tasks. So to start off, let's look at cognitive skills. In this work, researchers aim to identify what cognitive skills can be used to inform downstream tasks. And the idea is that we can identify latent skills that are translational across tasks, and then use that to predict the teleoperation or operation performance when you work with robots or other autonomous systems. You can have a person, give them a bunch of tests, get some metric for what their cognitive skills are at this time, and then use that to predict how they'll perform at robot tasks. We approach this through the objective of role assignment. So given 3 people and 3 robot operation tasks, which person should we assign to which task? And we operationalize this by developing a cognitive test battery of 3 cognitive skills, and then a series, a mission, you could say, of 3 robot operation tasks, where we would have 1 operator conduct each stage of this mission. We used some basic machine learning to construct a model to predict task scores from cognitive skill test results. So we collected a data set of participants taking these skill tests and then doing these robot teleoperation tasks. And we fitted regressions to each of these tasks and use those parameters to predict how well a new participant will perform at these tasks given their cognitive skill test results. So given no prior information about the user other than they performed this well in these tests, here's how we predict it will perform at operating in this robot scenario. We then conducted role assignments. So given 3 people, we have them all take the test. We then assign them to the ideal role to optimize the team's performance. And we framed this as an optimal assignment problem, and we called this, this method individualized role assignment, or IRA. We ran a user study. We got 29 people to complete our study. And then since the robot tasks were independent from each other, we were able to do a post-hoc analysis to make synthetic teams. So we can just take our 29 users and split them up into 3-person teams. We found that since we create synthetic teams, we can rank each possible assignment. So there are three people on the team, there are 6 possible assignments, and we can see where our method ranked. And we found that 31% of our teams were optimally assigned and greatly skewed in favor of better assignments. We also had a 24% improvement over our median scores, and 73% of our assignments outperformed to random. We tried this with larger candidate pools, and the results held. So to wrap up this first chapter, we looked at, can we predict a user's performance only with information about their cognitive skills? And the answer is yes. And we found that we were able to get a substantial margin over random assignment only with this information. All right, now to the good stuff. So our next research question is looking at how we can infer situation awareness by observing people and environments. And this comes with this concept that we as people use all the time called theory of mind. And as an example of this, I have a little skit. We'll see if you all can see it. Maybe not, it's all right. So imagine this. It's 8:30 in the morning, you're about to head to work. You get to your door. Phone, wallet, keys. Wait, where are my keys? Oh, of course, leave them on the counter. Every time when I get home, always put them on the counter. Oh, they're not here anymore. Someone must have moved them. Ah, here they are. You get to work. This is a scenario that I'm sure many of us have experienced, not being able to find something in the morning right when you need it, and then going through the stress that endures from that. And if I had a person near me who saw me trying to find my keys and see, okay, Jack's obviously trying to leave the house, he's probably going to be looking for his keys. Oh wait, I know where Jack's keys are. I assume that he doesn't know where they are. I can actively assist them and say, hey, I actually know where your keys are. What if we had that capability in robots? So people use theory of mind all the time. We're inferring what someone else is aware about their environment and using that to inform downstream tasks and planning and communication and so on. What if robots could too? And this is the guiding question of these next few works. As some terminology, the human factors community has identified several levels of how people represent things internally. At the top, we have simulation theory. And this is the idea that we maintain an internal simulation of our environment. If I throw up my clicker, I can project how it's going to navigate through the air, put my hand underneath it, and catch it. A part of a simulation theory is that you have a mental model. It's a formal structure of this internal simulation. How do I expect things to behave? How do I expect tasks to play out? And you can extend it to team mental models, say, how do I expect my teammate to behave and react to what I'm doing at this time? A subset of mental model that Ensley identified for human AI teaming is situation awareness. And this adds a bit more structure to this rather broad concept of mental model. And this is a person's understanding of the environment. And it's typically done along 3 levels. Level 1 is what objects are located where. Level 2 is the context of that. What does that mean on a little bit higher of a level? And level 3, how do I expect that to change in the immediate or far future? So there are 3 levels of situation awareness, and you'll hear that referenced later on. The objective of these works, or the work past my proposal, are can we infer a user's world belief state in real time to inform human-robot teaming capabilities? So can we predict this belief state or infer it and use that structure to inform downstream tasks? So we're mainly focusing here on level 1 situation awareness and level 2. So there's the knowledge of environment elements. And we think this is useful for several key activities: communication, estimation, understanding the context to better respond to questions. We suspect that if we know what someone is aware of, we can enable capabilities that are more representative of teammate capabilities instead of tool capabilities. And when we want to apply this to households or environments that have large open spaces, which is where we're trying to deploy robots to now, there are quite a few challenges that come up. First, robots have mobile cameras, and they also partial observability. They can only see what's kind of in front of them. Maybe they have a 360 view, but as soon as you turn a corner, you have no idea what's happening behind you or where you just were. And this causes a range of challenges similar to SLAM challenges, where things can move around or happen outside this observable region, and you need to resolve that. So that leads to the second challenge is object permanence. If an object moves and the robot doesn't see it, how can the robot identify which object that was? And most works in this space ignore this problem, either by saying if you see an object again, it's just a new object. You'll eventually have an infinite number of objects if this keeps moving around. Or they'll specifically label objects, be like all the bowls are all different colors, so you can have a nice one object per class. But that's not really realistic of households. And a third challenge is dynamic environments, where there are people in the environment that we want to deploy robots to. They can move objects around, they can relocate things, they can even like lie or mislead to robots. The robot has a lot of uncertainty as to what's going on in this environment and lacks that structure. And so we want to address all of these, and no one really has before. And so in these two works, we make some first steps towards solving these challenges and ideally setting a baseline that future people or future work can build upon. So our first step in this space looked at how we can infer user situation awareness in a partially observable environment. We've had this problem, we know we want to solve it. We're going to start off simple, 2D, abstract away the complexities of 3D and actual households, and just can we infer user situation awareness? We address this through a nice structure here. First had users complete a task with an autonomous agent. The agent then observes the user and infers what the user is aware of, so it infers their belief state. The users are then asked situation awareness questions. For those familiar, we followed the Saget format. And then afterwards, we have this data set of users going through their environments and their responses to situation awareness questions, and we predict what the user responses will be to these questions. And so our first stab at this was there are several frameworks that look into how we can use theory of mind in human AI and robot teaming. And so we were first looking at how well can current methods predict user situation awareness responses. So we took the overcooked domain, some of you may be familiar with it, it's a mess, and we made it partially observable and made this user study out of this environment. So for those watching at home, I blew up this video onto a larger size. So we made it partially observable, so the user and the agent can only see a region around their own agent, and they're trying to collaborate to do this cooking task. And so they need to put onions and tomatoes into these pots on the stove, wait for them to cook, and then bring a plate over to put the soup on the plate and deliver it to a serving station. And they're doing this collaboratively. We just used a straightforward state machine planner for the autonomous agent in this case. The users periodically ask situation awareness questions via the Saget format, like how many soups can be made, where's the nearest ingredient of this particular type, is there at least one available of an ingredient, and so on. And with that data set, we can then do our post and hoc analysis. We looked at 4 different layouts to try to evaluate this across a range of difficulties and several modes of the agent's perception. So we had one mode for the user throughout, so that it was consistent across our users, and we didn't have to have hundreds of users to evaluate this. But in our post hoc analysis, since we're just replaying through these experiments, we can look at different types of observability in different ranges. We had B type, which is 90 degrees centered on the user's normal, D type, which is 180 degrees, and O type, which is 360. And you'll see those letters referred to in the next couple slides. The number refers to the radius from the user. Here is the breakdown of the situation awareness questions that we asked. So we looked at how full pots are, the availability of ingredients, and say the teammate's location. Looking at that for level 1, so that's just where objects are in the environment. And we also asked level 2 questions: how many soups can be remaining? What is the state of pots? So adding a bit more context upon our questionnaire. And overall, there are approximately questions asked for each level, and a solid distribution across all question types. We then wanted to predict the user's responses to these situation awareness questions. So we designed this pipeline to go from the ground truth observations, filtering it by the robot's observability, getting all the way down to inferring the predicted user belief states using a recursive theory of mind here. And then with the user's belief state, we compare it to actual user responses and try to predict the responses to these questions. So given what we think the user is aware of, how do we think the user is going to respond to these questions? And this leads us to the false beliefs that we're looking for. On the top left, we see here's what the raw observation, here's what the actual environment looks like. We see that the user has put down a plate that's blocked in red. On the bottom left, we see what the user thinks the environment looks like. So given that the user is in partially observable space, this is an O type, you can see the 360 view. The robot has not observed the plate at that location, so it thinks that the user is still holding it. However, this then cascades to the robot's false belief about the user, where since the robot doesn't know the plate has been set down, the robot thinks that the human also does not know that the plate has been set down. And so these false beliefs are what we're looking at. And ideally, how can we have the robot have a better belief state or a reasonable belief state of the person so that we can predict what they're going to respond to when they answer these questions? To predict user responses, we looked at two methods. Logical predicates method, which is what most literature has used in space, and this is just hard-coded rules. If this, then this. We also, this was early 2024, LLMs were the big thing, I guess they still are. We fed in the scene graph to an LLM, GPT-4 in this case, and asked it to choose the most likely user response. And we were able to compare those responses from our hard-coded rules to just throwing into an LLM and letting its own prior understanding of how these environments could work and how users can respond to do this for us, so we don't have to make those rules ourselves. Our results here were that users performed pretty well. So it's good that users did perform all at 100%, otherwise there would really be no false beliefs. And they averaged about 60 to 80% on each route. The models were also about 50 to 75% accurate, so a little less than the user's performance. And what this indicates to us is that most of the error in this case was from user error, not really false beliefs. And this held across different layers of observability. So on the bottom right plot, you can see that as we decrease the observable region, so as the numbers go down, the score of our predicted user situation awareness responses stays around the same. On the bottom left, we have a comparison between the LLM and our logical predicates, those handcrafted rules, across a very large belief state and a very low. And we find that the findings were rather comparable. So the LLM was able to present responses to situation awareness questions that more or less matched what our hard handcrafted rules would return. And it's a good thing. It means, okay, we can just use the LLM to circumvent having to write these rules ourselves. But it meant that our domain was a bit too easy. So it motivates us for next steps. And also we're recognizing the limitations of this work. So overall, we augmented the overcooked domain to make it partially observable. We got this data set of user situation awareness responses. We compared these two methods at predicting how the user would respond to these questions. And our main takeaways are that there is a signal, so we can infer someone's user's belief state. We can use that to predict how they'll respond to situation awareness questions. And the layouts were also a little bit too easy. So we're keeping those in mind as we move on to our next work. So we finished this. We thought, cool, we can predict someone's beliefs quite well, actually. I mean, random here would be about 20 to 25%. So we're doing significantly better than random. And let's step it up, take it to the next level. And that brings me to the last contribution I have for you all today, and the one I'm most excited about, which is how can we infer a world belief state from camera observations in a household domain? So our previous work looked at a 2D abstracted environment. Let's bring it to 3D. Let's bring it to a household as close as we can get to a real world simulation. So the guiding research question again, how can we infer a world belief state in a 3D household domain? And really, we're only using the camera observations here, trying to remove any privileged information that we would not expect from an actual robot. And the overall structure, we have a robot that tracks objects in the scene. And then when the robot observes a person, we use the gaze direction of the person to infer what that person's aware of. And we believe that this belief state is useful for a broad range of downstream tasks, as we discussed earlier. And so if a person says, hey, robot, I am going off to work, we want the robot to reason a bit more in depthly. So say, okay, Jackie, named character Jackie, has told me that she's going to go to work. Wallets and keys are relevant for this activity of going to work. I think that Jackie knows where the keys are, but I don't think Jackie knows where her wallet is. So I should approach Jackie and tell her, hey, heads up, your wallet's over here, and do that act of assistance. That's what I wish had happened when I was trying to find my keys a bit earlier. And so the robot can rationalize this, use this internal characteristic or individualized model of the person, and then respond appropriately, your wallet's on the table. This is the ideal case when we're heading towards. So we took what we had previously in the overcooked domain, revamped it into 3D, made this cool system diagram, took a lot of work, but we won't go into those details all too much. Here's a nice visualization of what you were just looking at. So we start off with the robot's observations, the RGB and depth. Those are really the only active sensors that we're using for this work. We run object detection on this sensor information, as well as pose detection when we observe a person. You can see that the objects are highlighted based off their semantic segmentation. We then project the observations in the 3D space. So knowing the robot's current location, so we assume a localization stack, we can project where the objects are. So we're maintaining this semantic map as the robot observes this environment. We also had to resolve objects that are seen. So if an object moves in the environment, identifying which object that was, and we use just a minimum set matching algorithm for that. When we observe the person, we also infer their gaze region by doing ray casting from the location to objects in the area. It's a bit of a stretch for that assumption because object occlusions aren't considered, but in our household environment, most of the objects were below waist level, and so it made sense for our domain. We then combined the inferred gaze region and the robot semantic map to do this recursive theory of mind again and infer what we think the human is aware of. So this inferred human semantic map. Here's a video of this going. Start in a couple seconds. So we see the object perfect. This is all, there's no ground truth being used for the object detection or pose detection for that matter. We used LLV2, and this allowed us to do open vocabulary detection and made it a kind of zero shot, you could say, where we knew what classes were in this environment, so what kind of objects we were looking for, but we did not train or fine-tune the model on these objects in particular. So this could be deployed in theory to any household with their own objects, and the detection should work just fine. So as the robot navigates, it's constructing its own semantic map and updating, resolving which object it sees. And when the robot observes people, it identifies the pose and then gets the gaze region, the normal vector from the hips and the shoulders, to identify what objects we think the user is aware of. Between observations of the user, we use a trajectory generation algorithm. We use A star for this case. So between 2 points of seeing the user, the robot guesses what trajectory the user took between those observations, and then adds all those objects that it thinks the user would have seen to this inferred human map. So going back to the system diagram, we have our object detection, our pose detection. We predict we do this trajectory estimate for how we think the user navigated between observations. We combine this all together into this inferred belief state, and we resolve it using this a minimum distance between set resolver for when we observe objects, identify which object is being observed, and to resolve dynamic objects. So we have this inferred human map. Great, awesome. We also can get we can assume the human's map if we, since we're running this in simulation, we can say if we assume the human has perfect perception or some model of it, we can then get the actual human map throughout this scenario. But we need some way to evaluate how well we do. Every study needs an evaluation. And so our next question was, after we build out the system, how can we measure the disparity between two belief states? And our belief state here is really a set, so just a set of objects and their locations and the class of each object. And so we thought, okay, we're in a household environment. Are there any other complications that this entails? And it turns out there were. If a person says, I need a cup, do they actually care about which cup it is, or do they just need a cup? And that was a bit of a motivating question for us here. So if you have 5 cups and you say, okay, I need a cup, does it actually matter if 2 cups are swapped? So if we have 5 cups and locations, someone uses one, replaces it with another. Would that actually affect the user belief state? And is that something that we want to track? And our answer was no. So we need a disparity metric that is instance agnostic. So it doesn't matter which cup is where, just that there is a cup if they have the same class. And this led us to design this metric called sum minimum cost by class, the minimum distance to resolve objects of each class. So it's a rather straightforward set distance metric. So you split up your belief state into the subsets for each class, and then find the shortest distance to map object locations from one set to the other. So this assumes that all objects of a class are the same. And so if you swap 2 objects locations, it would not affect the sum minimum cost. And this was how we could rationalize this household domain issue of doesn't matter which cup you see, just that there's a cup there. And so there were 3 figures of merit that we were interested in evaluating from this work. The first is, well, the robot's performance. How well can the robot's belief state, how far away is the robot's inferred belief state of the human from the person's actual belief state? So a low distance here means that our system is working well and we are accurately inferring the user's belief state. Second, looking at the distance between a person's belief state and the true world state. So if this value is high, it means that the environment is complex enough that the person can have false beliefs. So this is how we can make sure that we're avoiding a limitation of the previous work. And third, looking at the robot's belief state relative to the true world state as well. If this value is high, it means that the environment is too complex for the robot, and it can struggle to maintain an accurate map, which can then lead to incorrect downstream recommendations or activities that we use this information for. We then evaluate on a scenario we call parents are out. So in this scenario, Jackie starts in a clean house, perfect, correct belief state. Jackie knows where everything is and says, okay, I'll be back in a bit. While Jackie is gone, Jackie's kids throw a party or something. They scatter everything is randomly shuffled. So now Jackie is gone. Her belief state is still at the house in its initial clean state. However, the kids have moved everything around and the objects are shuffled. Jackie then returns home, sees, oh my gosh, the house is a mess. What am I going to do? And does a quick walk around to assess the situation. The robot then follows Jackie and maintains this prediction, this inference of Jackie's belief state. And so the robot knows what the house looks like. Jackie starts off with a very incorrect belief state. As Jackie moves through the house, Jackie's belief state improves. So the distance between that and the initial state decrease. And the robot's trying to maintain its own inference of what Jackie's belief state is.
Jack, can I quickly ask you a clarification question?
Of course.
So in the previous slide where you're setting up the experiment, I'm curious about the robot's belief state. So does the robot know accurately where the objects are currently?
Yes. So the robot has been in the house while the kids are moving everything around and has an accurate belief state.
Perfect. Thank you.
All right. So we get to this scenario then. We want to do some reasoning out of this and use it for a downstream task. So say Jackie does her walkabout, and she then says, okay, I need to make some tea. I need to figure out how I'm going to clean all this up. We want the robot to think, okay, I've been keeping track of what objects Jackie has seen. I have this inferred belief state. I know what objects are relevant for making tea. I know that Jackie originally thought that the kettle was here when she left the house. However, now that she's back, the kettle has moved. I don't think that she was aware of it now. So I'm going to notify her of that. This active assistance task. We ran through this using virtual home. That was a simulator that you saw used a couple slides ago. And the gray areas here refer to frames in which Jackie is observed by the robot agent. So first, we were interested in what is the baseline error? What is the error from the simulator, our perception stack, and our belief state resolver? So if the robot navigates through the environment, nothing is moving, how much error are we going to get? And this is a nice baseline for are we doing better than 0? And so we found that just to get an understanding of where we can ground the numbers here, just by walking around, our resolver had an error of 0.2 meters. So on average, it thought objects were on average 0.2 meters away from where they actually were in the environment. Then we look at what Jackie believes. So Jackie initially came back and the environment was all shuffled. She knew really nothing about where objects were. And so we initially start off with a very high SMCC, a very high error because she hasn't observed the objects yet. As Jackie walks around the environment, that error decreases. And so ideally, it would eventually converge as she's navigated the environment enough. This simulator only runs for about 60 seconds before crashing, unfortunately. So we're able to get this about minute-long window of navigating through all the rooms in the household. We then look at what we're most interested in, the error of the inferred belief state. And so the distance between our inferred belief state of Jackie and what she actually thinks. And we see a nice distance between that, which indicates that Jackie's belief state of the household is worse than the robot's inferred belief state of Jackie, which means that we can use this for downstream tasking and identifying and resolving false beliefs. And so as expected, as Jackie walks around, the belief state improves. Jackie is not seen for all points in this scenario, rather sparsely actually. And so we're getting this nice chaos that is representative of actual households and where we expect to deploy this to. Our main finding here, the inferred belief state, the error of the inferred belief state is less than the error of Jackie's belief state. And so we can use this to resolve false beliefs. As an ablation, we compare this to using ground truth sensory information. And you can place spot the difference. You might have a bit of a challenge, but they are different graphs. There are very subtle differences. And we'll explore this on the next slide as well. We find that our perception stack is actually quite good. We are doing about as well using our perception stack as we would if we were using ground truth perception. We ran an ablation study where we replaced every one of those main components. Yes. It's because both agents have partial observability. So if I observe you and you're looking towards the screen, and I haven't looked at the screen, if things in this area inform your belief state, I wouldn't be aware of it because I haven't fully rationalized that.
Hey, Jack, sorry. If somebody asks a question in the room, can you please repeat it? I can't hear them at all. Thank you.
So why there are big drops and right, and why when the agent when Jackie is visible, where there aren't major changes. And so for the big drops, let's see, it's really when the resolver correctly resolves had been previously misresolved, from my understanding. So these big jumps are when the resolver incorrectly resolves an object, which causes a large error. And then by chance, if the resolver ends up fixing that as it gets more information and observes the human more, we see a drop as that corrects. So these big jumps are one individual object that then gets way misplaced because of this inference. Okay. Any other questions before I go on? So we compare to ground truth perception. We find that we're doing quite good. I'm very happy with this. We ran an ablation where each of these components is ablated to ground truth baseline and with a full perception stack baseline. And we really find negligible difference between the ablation conditions, which means that for this domain, and there are some characteristics we can go more in depth there. For this domain, the difference between what we're able to do with modern perception tools and to the ground truth, we're really quite negligible. I'm very pleased with that. So we have this ability to infer belief state. We find that relative to ground truth, we're doing pretty good, at least with our methods. We have this simulation domain in a household where we have this task that we have this parents are out activity, and we want to use this now for a downstream task. We have this infer belief state. How can we use it? And so there are really two steps here. We first need to identify what the false beliefs are, and then use that information to correct for them. So we frame this in this task active assistance. To identify what the false beliefs are, we filter in objects that are far away from any objects of that class in the robot's belief state. So that looks like a lot of math and technical terms. So I have a nice visualization here for you. If you have beta robots, this is the robot's own belief state, and you have the inferred belief state of the human. There are some differences that we're interested in. So you see most of the dots rather closely aligned, and there are a few that are quite far from where we expect the human to be aware of. We can identify the dots that are far away from any object in that class. And our motivation for that is if you're looking for one of those 5 cups, it doesn't really matter that you know where every single one of those cups are, just that you can find one if you need it. So we're most interested in assisting a user when we think that they have no idea where any object of a class that we think they're looking for would be located. We took this filtered down belief state. We call this the unobserved objects. And we ran it through a quantized Quen model. We were interested in using local compute for this, just for privacy reasons and just to see the capabilities of these models at the moment. And we tried 4 different methods. First, we put all the objects to the LLM and asked it to identify which ones are relevant for this activity. And the prompt's here, but we can skip over that for now. We then looked at a chain of thought approach using a single object. So running this for every object in our comparison. So saying you're tasked with judging whether this object is relevant, give an example, and then say, your turn, is it relevant? We tried a stripped down version, just quite simple, low context. Is this object useful for this activity? Just answer true or false. And while we were developing this work, some models came out for zero-shot classification with using a DiBerta model, fine-tuned for zero-shot classifications. We were like, let's try this as well. And so we gave it a source, gave it does this sentence make sense? Does it not make sense? And use that for our classification. There might be better ways of approaching this, but it was our first shot in this approach. So we evaluated the F1 precision and recall of doing this across every 100 frames. So every 10 seconds, we would look at what objects we think the user is not aware of. We had a list of activities. We have our ground truth, just researcher made mapping between what objects are relevant for activities, and then deduplicated that and ran it through our system here. And we found that overall, our methods greatly outperformed random. However, there wasn't really a clear winner. I was surprised a bit at how good the classification embedding module was, because it has a greatly reduced computational cost, but it inspired us saying, okay, we can do better than random. Let's try to take a little bit further and see what we can do here. For those unfamiliar, precision is looking at whether notifications are correct, and recall is looking at all the relevant items for a task are being correctly recalled. So we spoke with some friends who are very good at using LLMs, and they said, okay, this is fun. Quantized models aren't really the best, but you should try looking at logits. And so we reran this using Quen 2.5 instruct again. And instead of getting the whole output and trying to do constraining the output to using OLAMA or LangChain, we looked at the logits directly. So getting the confidence score for yes and no pairing, running it through softmax to get the confidence in this response. And we were interested in a variety of different yes-no pairings, like true, false, yes, no, capitals, not, seeing what other tokens we can use here. Using our single binary prompts, this is just is this object useful for the activity? We actually found quite an interesting variety or a range of confidences using different pairings. And overall, we had an F1 score of around 0.55, 0.56. So originally, we were at 0.46. We were able to increase that by a margin. Our finding here is that the F1 scores were a bit higher, but it came at a cost of lower precision. And that's really just because of where we set our confidence threshold, 0.5 in this case, but we could tune that if we wanted to. We then looked at the chain of thought prompts. So this is just every object to every activity, giving a description of the task, giving it a symbolic example, then asking it. And we found that the results were quite a bit better. So we went from around 0.55 F1 score to about 0.75. And this aligns with prior work. Chain of thought is really the way to go when doing these evaluations. As a bit of a joke, we used Verity and Ney as one of our token pairings and found that it worked okay. Had actually a recall of 1, a bit surprising. And so from this work, we looked at, can we infer a real belief state from camera observations in a household domain? And really the answer is yes. We can use this theory of mind recursively to infer what someone is aware of. We've shown that we can use it for downstream tasks, greatly outperform random, and that modern semantic reasoning methods, i.e. LLMs, are rather good at reasoning over real belief states, and that perception stacks are able to do so with minimal setup costs. So all we had to really do was map a house, identify what objects we want to track, and we can use open vocabulary models for doing so. So that leads to future directions. There are a few ways that I wish we could have explored more in this work, but we're limited by current tools. So if any of you in the audience are looking to get into this space, I have 3 awesome ways you could help. First is looking at better simulators. Our work was limited to about 60-second rollouts. This was just a limitation of using virtual home, and there really were no other better semantic relocation simulators. I think this is a major area of work that's needed if we want to advance further in this space. Second, looking at semantic scene graphs. Object permanence is really a barren field. We had to construct all our resolver from scratch and figure out how we were going to approach that. And current methods that are similar don't approach the level of object permanence resolving that we would have liked. And last, modeling user perception. Models for how people remember things, how long an object has to be unobserved for people to forget it, the probabilistic nature of that hasn't really made it to the HR community yet. I would assume there's work being done in the cognitive science community, but it hasn't made its way to useful models for us here. And so in our case, we assume that user agent has quick perception. However, if I were here for another couple more years, hopefully I won't, we would have explored more individualized models to enable that teammate capability. So to recap, we start off by looking at cognitive skills, and we can predict someone's future performance at teleoperation tasks. We then switched gears to mental models, looked at how we can infer users' responses to situation awareness questions in a 2D environment, and then brought it to a 3D environment, wrapped that, fixed a number of the assumptions that we made for 2D, and evaluated how well we were able to perform in that space using what we can currently get off the shelf. And so tying it back, my work has looked at how we can model a person's cognitive state and apply it to inform human-robot team capabilities. And beyond these 3 works that I mentioned, I've had amazing collaborations that have explored a much broader teammate capabilities in this space that I wasn't able to get to today. So here again is an overview of all the projects I've done here. And we only talked about 3 today, but all of them are incredible. And as someone who's about to graduate, people keep asking me, what's next? I'm excited to say that in 2 months, I will be starting as a research scientist at Apple. And they won't tell me anything about what I'm doing, but given that they reached out and said, hey, we like your work, come work with us, I assume it has something to do with the stuff you've seen today. I want to thank all of my incredible collaborators, lab mates, advisors. I've had really 3 throughout these 5 years. And of course, more than anything, the amazing friends I've made along the way. You all have made this the best 5 years of my life, and I could not have asked for a better group to share this experience with. Thank you.